Hey, good afternoon, everyone. So we're very happy to have the third talk for this afternoon by our own Urs, who is going to tell us about higher topos theory in physics.
Thank you very much. Right, so by some synchronicity, I think what I'm going to do is I'll actually give the introduction to the previous three talks, especially aimed at
David, how do you get to
It'll go away in 30 seconds, or you can go to the keypad and press hash.
Yeah.
It's
Great. Thanks.
So as you can see here on this page, I was recently invited to write an entry for the second edition of the Encyclopedia of Mathematical Physics on the topic of higher topos theory in physics. Peter happens to be the section editor of what's called topology in physics.
Section.
Yeah, topology section. So there will be different sections. It's going to be a large book. And so so I was asked to give an encyclopedia entry for aimed at mathematical physicists. So what I'm going to say is aimed at people the way it's written. So I'm just going to present this encyclopedia article to you. Actually, I don't have slides, but I will go through some nice formulas. I hope it's aimed at people who do not possibly know what a category theory is. So I'll try to be very elementary. It may be really boring for some of you. At the same time, though, as we go along, it should also work the other way around. It should explain a bit what this category theory that you're all familiar, or some of you are very familiar with, got to do with mathematical physics. So maybe you can read it that way around. But it is going to be elementary, even though I don't want to downplay that too much, because I do think there's some very elementary ideas that kept being mentioned in previous talks, which are rarely amplified as to what they are. And making them really explicit helps not just laymen, I think, but also us experts to see in bird's eye perspective what we're actually doing. Okay, enough of an introduction, so let's dive into this. Hope this works now. So I can't see half of my screen here because of this thing. Can I put this away? Let's see. Oh, very good. All right. So, okay, I don't have to recall what a category is. What I do want to emphasize is this table here. So as you may have seen in physics, much of the success of mathematical physicists comes from being extremely naive and not bothering about it and just going ahead. So they write down coordinate expressions, as they used to do for their fields. And at some point, somebody says, hey, wait a second, let's just declare that these two coordinates actually do not commute. They pick up a sign when we commute them past each other. So everybody says, oh yeah, that's a great idea, and they just proceed. So what happened was, it was just some algebraic manipulation on paper, and after a while everybody gets used to it, and now you're operating on things that are denoted by symbols. They pick up a sign when you commute them, and you somehow pretend you know what this means as a geometry. Then people started saying, oh, these are coordinates on a superspace, and or maybe these are classical fermion fields. So what I'm trying to say is, you make very naive local computations, and kind of cross your fingers that this makes sense as a global geometry. And the theme of what I'm trying to present here is that this actually does make perfect sense. So the success of this method, naive as it is actually due to the existence of topos theory. Namely, we can understand this. I'm trying to explain this. This is the first part of this talk. Actually, we're just going through very basic examples, just in one topos theory, actually, of what these coordinate operations do. And the running theme will be that I'll claim that what physicists actually do, they work with small categories of little probe objects, of generalized coordinate systems, really. And these arrange eventually into a site, which when you form the sheaves on that site, it gives you the generalized spaces, the actual global spaces that are sort of locally modeled on these naive models. And that simple idea, just naivety mixed with a big machine, actually turns out to be super useful and effective. And that's the theme of this talk. So if we do get time permitting to the end of this, I'm going to go sequentially through this list. Start with the ordinary coordinate charts, RNs. These are exactly the RNs we saw in Adrian's talk, with the local models of differential topology, if you wish. So this is the familiar bit, but I'll spend some time motivating with this familiar coordinate charts, this notion of what does it mean to this generalized space modeled on these things, which are just those infinity stacks that Adrian was talking about, but I'll try to motivate a bit in which sense these are models of good generalized spaces that one might actually want to use in physics. And we'll see some examples for space-times, of course, but also modular spaces of forms that will contain anomaly polynomials, for instance. So I'm going through a list of stuff that actual physicists recognize and should care about. Then maybe I'll mention passing. I don't want to dwell too much on this. infinitesimal versions of these. This is kind of a stepping stone towards the super geometry, the fermionic geometry, which is a special case actually of infinitesimal coordinates where these signs that I was talking about are being picked up. And then after sort of half of this talk, I'm gonna look, there's two kinds of particles that make up everything around us and ourselves, fermions and bosons, right? Fermions have this funny property with the sign that we're capturing by these superspaces here, whereas the bosons have this funny property that for them the notion of equality gets relaxed. In general, you can have two nominally distinct bosonic field configurations, which are nevertheless identified by a gauge transformation. And that's where the homotopy theory comes in. So the claim here is all this homotopy theory we've been hearing about very much. It's really what in physics is known as the gauge principle, the gauge symmetries of bosonic fields. And then, yeah, time permitting, there's some more refined versions here where we bring in equivariance and maybe stability, and with that, finally, the actual quantum aspects of physics. But we'll see how far we get. So that's the plan. And I do want to motivate this very elementary perspective here, which was implicit in previous talks. It's just being used. We heard about stacks, we heard about sheaves. I want to highlight the way you should think about these things from a physics perspective. So the idea is very much a physics operational approach to what is a space. Suppose we want to describe physically the space around us. How do we actually, if we think of the actual biological way of interacting with this space, how do we know that this is spacey? Well, in one way or other, we probe it, right? This space doesn't appear to us as a set of points equipped with a sigma algebra of open subsets. That's not how we perceive this space. The way we perceive this space is by probing it, right? And so I stretch out my arm and I see, oh, here's something. Or in general, of course, I probe by light photons that run through here. So there's something that gets into the space and somehow I can in some way detect what it does. And that simple idea, that intuitively accessible idea, is going to lead us actually to the notion of sheaf models. So what we want to say is let's forget this notion of smooth manifolds as being prescribed sets of points which are locally isomorphic to a coordinate chart, and look at something more general. Let's suppose these coordinate charts, by which I mean abstract coordinate charts, but I mean these abstract RNs. Let's suppose we want to talk about a space which I probe by Rn. So there's some abstract space which I don't actually know yet what it is, but I'm going to pretend now that I know how to probe it, how to map an Rn into it smoothly. So that's the idea. I want to describe a would-be space X, not yet defined, by saying for each probe space, what is the set of ways of probing it? And for that to be consistent, I'll demand just a handful of consistency conditions, and that will make it a sheaf. And what comes now should be intuitively accessible. But let's just briefly look through it. So I have it here in prose, but I'll just look at these pictures actually. So
by plots, you need to be vague. Plots are just
right. So
maps
are
just
right.
embeddings.
Right. So the idea is now I'm going to bootstrap a notion of a space X into existence by telling you what it would mean to plot out an Rn inside it. So exactly. So in these diagrams now, whenever we have an arrow from an Rn, from a coordinate chart to this X, this is, I should have made it dashed maybe. This is like a would-be arrow. That X does not exist yet, but I'm going to tell you, well, there is one way of mapping Rn into X, and I'm calling it phi. That's information I give you. In fact, I give you the whole set. This is the set plots from R to X. I give you a whole set of these phi's, and you should be able to reconstruct or understand the space from these systems of sets of possible probes that I give you. But just these abstract sets won't help you. Well, you will have to know how they relate to each other as you move your plots around, right? So that you can actually plot out something. So moving around, one notion of what it means is, well, if we do have a smooth map, an actual smooth function between these Rn's, then we should be able, and we do have one of these plots, right? Then there should be, remember this does not exist yet as a map, but pretending that it does exist as a map, we should be able to pre-compose it with F to get a plot phi after F that goes directly, right? And then if we have a second smooth function here, we should be able to pre-compose that too. The evident consistency condition is, well, that end result here of putting back twice should be the same thing as taking the original plot and pulling it back along that composite. So that condition makes the set of plots, this pulled Rn, pre-sheaf on the side of smooth manifolds, which in Adrian's talk was called, what was it called? Diff infinity? No, the side, I don't know. Card infinity.
The site is called.
The site here is card infinity. So for me, it's card space. Cartesian spaces are smooth maps. So that is the first consistency condition of these plots. They should be pre-composable with smooth maps. If I have one plot, I can kind of move it. And this should be compatible under composition. And identity should be, I'm not showing this here, identities should act as identities. Then the second condition is what's going to become the sheaf condition. This just means, suppose I have a big plot. So I have this big coordinate chart here. I lay it out in the space. I see, so it's in the space in some way. But now actually this coordinate chart, I can cover it, say, by two patches. I'm calling them U1 and U2 here. U1 and U2 are themselves Rn's, but I'm not calling them Rn because then it becomes confusing. So U1 is, you can say it's maybe 1/2 space over n with a little overlap. And U2 is another half space over n with a little overlap. And so they cover, so I have this big plot here, but that means, well, if I cut them in half, I have one small plot and another small plot that happen to coincide with the overlap. And so I want to impose the condition that whenever this happens, there's a bijection between these global plots and the tuples of smaller plots that agree, which is what this diagram is trying to show, right? So here's the global plot on Rn. Here's one on, say, 1/2 space, and another half space. If on the intersection they agree, then these two plots should uniquely characterize this total plot. So this gives a notion of locality of these plots. It says, plotting out this space, really, what I really want to do is, we'll come to this in a second, I really want to be able to plot out a tiny little bit like a germ of a piece of space and be able to patch them together to get a picture of the full space. So that's already, these two conditions together are define sheaf on the side of Cartesian spaces. But the way I've presented it, they also define the space X, or at least some form of it. We'll see in a second, they actually give a good idea of that space X. But since we want to make these spaces defined by a live in a category, I'll just say what the maps now are. So I have now a generalized notion of space, which I only know by how I'm probing it. So now I want to know what does it mean to have a smooth map between two such indirectly defined spaces. Well, in that same spirit, I'm saying, well, okay, I don't know what that map actually is, but I can sort of probe that map now. Whatever that map is, it should be such that if I do have a probe of my source space, the map should take it to a probe of the target space. So that's what this picture is trying to show. Here's a plot of X. Here's this would-be map from X to Y. Oh, I see, sorry. Thanks. Oops, I saw it. All right, so if I have a plot, I have this would-be map, I should be able to get a new plot, which is this here, now of the target manifold. And again, this should be compatible with pre-composition. So this diagram should commute. If I first apply this to the plot and then pre-compose the plot with a smooth map, it should be the same thing as well. So some evident consistency condition. Now, this gives us a category of what we call smooth sets. This, by the way, for anybody who has seen, of course, Gregory's last talk in the GDP seminar, this is exactly what Gregory also started his talk with, so I'm just repeating that. And so we say in the Topos theoretic language, this is just jargon now for the hopefully kindergarten idea that I sketched here. We say that's a category, it just means the collection of all these generalized smooth sets, these smooth spaces with these maps between them. We call it a category. It's called the sheaf category in jargon on Cartesian spaces, smooth Cartesian spaces with values and sets. And if we forget this condition here, then we're calling them pre-sheaves. So if you just have this condition, it's a pre-sheaf. And so we say this category is a full subcategory of the pre-sheaf category. Now, the basic example is the representables. So every Cartesian space itself, and more generally every smooth manifold, is among these generalized smooth, right? We want to have some examples now of these generalized smooth. So you're asking, okay, can I get an idea of what we actually define now? Well, yeah, first of all, every smooth manifold, M here, becomes a smooth set in this previous generalized sense, but just by declaring the set of plots to just be the ordinary sets of smooth maps into it. Right? And R infinite and Rn is a smooth manifold. So there's a standard notion of what it means to smoothly map Rn into M, standard notion. So take this to be the plots. So these are the default examples. And it turns out, as we'll see in a moment, that this is kind of the first important aspect of this construction. that not only do I have this construction, but it gives a fully faithful embedding of smooth manifolds into these more generalized smooth sets. So this means essentially that roughly that everything you used to be doing with smooth manifolds will continue to hold more or less in smooth sets. Now, one important aspect is now that our ends are regarded as smooth sets, we can suddenly do something that we couldn't do before. We now have these maps actually, or we have such maps, right? So with Rn, where do I have this here? So now that Rn is understood as a smooth set, and we understood morphisms of smooth sets, I can now say, well, what if this arrow here, which used to be this abstract plot, is an actual map of smooth sets? And you see, oh, at this point, we're actually running into trouble because, why would that be the same? So probably, you might think, these, this map understood as a map of smooth sets, maybe it's just not the same as the actual plots are defined. There's a potential inconsistency here. And I think this is a fun perspective on this matter. The fact that this is not actually an inconsistency, but that these two notions now do agree, which means that our bootstrap definition is actually successful. That is nothing but the Yoneda lemma. The Yoneda lemma in category theory says that the homomorphisms of sheaves, namely of smooth sets from this representable, from this probe space into X, are actually canonically in bijection, natural bijection, to our prescribed plots. So what we just wrote down as a wish list, what should be smooth maps, now actually are the smooth maps, and exactly that. That's a basic lemma, which you probably have heard of. One reason why it's so often mentioned is not because it's hard or something, but because it's so fundamental. For instance, in this case, the Yoneda lemma, or from this perspective, the Yoneda lemma says that generalized functorial geometry, this really Grothendieck's perspective, as was mentioned previously today from 1958, where he said we shouldn't think about schemes as being locally ring spaces. We should think of them in terms of their probes. We call it the functor of points. That this perspective is consistent. That is a unit. Another important basic fact that very much appeals actually to the physical intuition of what space is the following fact, which holds for the. So this will not hold fully generally for all toposes. This holds. We have enough points of. So anyway, but it does hold for all sides of Cartesian spaces. Namely, it turns out that after we've defined these spaces with these big plots by laying out coordinate types, actually, as I mentioned before, the only thing that turns out to actually matter are the germs of plots. So it's going to be sufficient to probe our spaces just by the tiniest probes, as long as they have any dimension. So the formal definition is the germ of a plot, so forming the set of plot germs, this is plot germ, is the quotient of all the plots on Rn, quotient by the equivalence relation that regards two plots as being equivalent if restricted to some open neighborhood, some open ball of any point. So I'm choosing the one that has a name, which is the origin. If the restriction to any open neighborhood coincides. So if they coincide on any small neighborhood of 0, I say they represent the same germ of a plot. And then one can easily check, because this is actually a co-limit here, blah, blah, blah. And so one can check easily that our maps of smooth sets, which remember were defined by taking plots to plots, well, they in particular restrict now to sending germs of plots to germs of plots. So every such smooth map gives a function between system of functions for all Rn between the germs. And the theorem is now actually that this detects everything about a smooth space. And the way we phrase this in formal language uses this notion of localization, which was already mentioned in previous talks, just in passing. So let me just say it again. So let's say a smooth map between these generalized smooth sets is a local isomorphism if for each type of plot, each dimension, it induces bijection on the germs of plots. Right? So this means at least two spaces, maybe I have to find them differently. But if just the smallest possible probes of this space, if bijectively map to the smallest possible probes of this space, well, then I cannot distinguish these two spaces. I'll call them locally isomorphic. And the theorem then is that the category of smooth sets has another incarnation. We define it as the category of sheaves, but we can also say It's actually the category of presheaves without that gluing condition. But then we formally say every map that is a local isomorphism, let's force it to become an actual isomorphism. If we identify those presheaves without the gluing condition such that it becomes true that the smallest probes are sufficient to see anything, we get the same category. I'm mentioning this here because this is going to be this, as opposed to the previous case, is going to be our road to the higher versions of this stuff. So it may seem a bit more technical. I don't know how it feels when you see this for the first time. Of course, others it's boring. But let's maybe just say it again. We have these spaces. We want to force the infinitesimal probes, or the germs of probes are sufficient. So we just localize, just as one does with the ring. We formally invert some of these maps to make them reflect this principle. Okay. So that's it. That was the notion of a sheaf topos motivated from this idea of a smooth set. And now the nice thing is a general topos, by which here, as usual, I mean Grothendieck topos. That's better or worse. Another slightly more general notion of topos, which I'm not going to talk about. The elementary topos, topi. It's just this, a category. I mean, this is just as a side maybe, just to justify the title of this text here, actually. So general call it category. Grothendieck topos, there is some small category with some notion of what it means to cover its objects, such that in direct analogy with what I've just shown, we can form these sheaves, and these categories are equivalent. So from this perspective, if you wish, this is of course just one perspective on topos theory. There's many perspectives, that's why it's called the elephant, right? But from this perspective, topos are exactly the categories of probable spaces. Okay, so let's pick some fruit of this. Here's the first, it's again super simple for those who know this, but it's actually important to highlight for those who have not seen this. The first application of what topos theory does for physics is the following. So one reason, of several maybe, but certainly the first major obstacle that physicists ran into actually 100 years back, when they tried to generalize mechanics, or maybe 200 years back, to field theory, is that in field theory, the basic configurations, so that the spaces of all collections of field history that you're looking at are mapping spaces. So field theory is called field theory because its objects are fields in the sense of over a space-time smooth set X, you have a map that I'm inclined to say that sends each point to a field value F, but we shouldn't actually necessarily think of this way because we didn't define X to be a set of points. But in any case, it's a map from X to F. That would be, for instance, if people speak of a scalar field, like a Higgs field or something, then F would just be, say, the complex numbers. We just have this is a simplified picture of the Higgs field. And we just have this map here. Or if you're maybe more interestingly, we'll come to this, if you have a spinor bundle over space-time, then such a map might be a section of that spinor bundle, which to each point in X finds, I said it again, finds a point in a spin representation, and they would be a spinor field. Anyway, so these fields, and the subtlety is for differential geometers and then physicists by extension, is that now, where should I point? Yeah, I could just point here. That now this means that our collection of fields is a mapping space. Somehow we want to be speaking about not just the set, but we want to do a differential geometry of this, like variation and calculus. We want to be speaking of the smooth set of all maps from X to F. And this is actually subtle, because unless you put some pretty wild conditions on X and F, this thing is just not going to be an object of differential geometry. So if X is actually compact, which is not a good assumption for a space-time in reality, then you can work hard with your functional analysis, and if F is a manifold, and put the structure of an infinite dimensional Fréchet manifold on these mapping spaces. So with lots of work, you can cover an unrealistic case, and then you have a hard time working with it because it's not easy to work with Fréchet manifolds. If X is not even compact, or if F might be more wild, like for an actual gauge theory, F itself wouldn't be quite a manifold itself, then this mapping space is just nothing like what you can find any help for in a differential geometry text. But now, armed with our new insight of not worrying about these point set models that people get stuck on, we're just going to say, well, okay, is it maybe easy to probe this mapping space? And it turns out it's super easy. So, let me sketch the definition of Cartesian closure. Sorry, this is really kindergarten stuff that I'm doing, but it's maybe important I'll say it anyway. So let's just think about what would it mean to probe? So again, U here, you should think of it as being now an Rn, but I call it U not to get confused. It's some probe U, and we want to ask, okay, what's the U-shaped plots of our mapping space? Well, let's just think of it for a moment. What is this mapping space? So a point, an element in this mapping space should be a field phi, and as such, it should map from X to F. And now, if we have a plot of such fields, well, it somehow means that okay, every point in U needs to get mapped to some of these fields. So we have a U parametrized family of fields, right, which are just called U maps to phi of U. But phi itself was a map from X to Y. So it just means actually that from this I can get a function of two variables that reads in a U, at which point in parameter space are we, and reads in an X, at which point in spacetime are we, and then it returns the field value at that spacetime value for that parameter plot. So this is a very basic currying junction, the internal Holman junction. But it's actually good to think of it from this physical perspective, because this is exactly how physical fields are being used in families, as one says. And so you see, you can take this to be a definition. We say, well, since this dependence here on U and X, since all of these spins are meant to be smooth, and we know what a smooth function from a smooth manifold to a smooth manifold is, we just declare this to be the plots of this a priori very scary and out of reach smooth thing here. So we know exactly what a plot of the smooth mapping space should be. It should just be a function of this product, a U parameterized function. And that defines, you can easily check this as a sheaf. So this definition defines the mapping space. And now the remarkable thing is, which we already highlighted in his talk last week, or maybe 2 weeks ago, I forget, is that this super, I would say, intuitive, obvious, certainly categorically very elementary definition subsumes faithfully all the other definitions if they apply. So if your spacetime X, if it happens to be compact, or you're assuming it to be, so that there is a Fréchet manifold structure in the mapping space, then that happens to be actually equivalent to or equal to what I just described under the embedding of Fréchet manifolds. So I don't know, did I actually say this anywhere? So Fréchet manifolds become smooth sets by the same formula as manifolds do, that you just take their plots to be the actual smooth functions in them. Even more generally, people devise, since Fréchet manifolds go on far enough, they devise the notion of ecological spaces, and that also concepts. In fact, that's my next statement. Let's just look at this for a second. If we still have the energy, you have maybe to tell me if this gets too boring. Let's see. So remember that we did not define these smooth sets as being, as in the traditional way, as being point sets equivalent extra structure. We didn't say anything about points. Well, sort of we did. We could say there were the plots by R0s that are kind of the points, but they didn't we didn't impose that this kind of underlies the space, but it could happen. Let's assume it could happen that we have a smooth set where there exists an actual set, I'm calling it X subscript S for the underlying set, such that all the plots into X are naturally, the sets of these plots are naturally contained inside the actual maps of sets. So this means from the underlying set of Rn to XS. So in this sense, all the plots are actual maps of sets satisfying some smoothness condition. And if that is the case, so the category theorists would call these smooth sets concrete for obvious reason. These are things that are supported on their points. We'll see an example of a non-concrete thing so that you get a feeling for what this means. But following Soriot and then Patrick Iglesias and Moore, they also call diffeological spaces. It kind of comes from a different school of thought, but it converges to the same idea. One interesting aspect of these diffeological spaces is they contain all topological spaces in the delta generated form. So delta generated is a bit like compactly generated. It means topological spaces whose open subsets you can detect pre-images of maps from Euclidean spaces. It's a slightly smaller subcategory than all topological spaces, but it's large enough. It's a convenient category for doing topology. And they're faithfully subsumed. This is kind of amazing now because we're a priori doing smooth geometry here. But by the evident formula, which now says, well, suppose you have such a topological space, d-topological, take its plots to be just a continuous map. So you can certainly do that. We can say here's something whose would-be smooth functions are actually the continuous functions. We have that freedom now, and it turns out that again is actually a faithful embedding. It's a non-trivial theorem, but that turns out to be the case. It's actually faithfully embedded which will be useful later on when we do K-theory and stuff, because this means that typical classifying spaces, they're not smooth manifolds, all faithfully in here. Here's what I want to highlight now to get a, to show some new stuff that exists now in this more general notion of smooth sets. So we've seen now, or tried to argue that with this general notion of smooth sets, essentially everything you already knew faithfully sits in there and works nicely. Here's something that is not in the standard differential geometry textbooks, and it solves an eminent problem actually that physicists in field theory run into related to anomaly polynomials. It's just an example as an application. So let's look at this. Here's a non-concrete smooth set, namely I call it boldface omega p round forms. So we just define it. So this is meant to be the smooth classifying space of differential p forms. So what should that mean? It should mean whatever it is, its plots on an Rn should just be the set of differential forms. You should think of this, the way you should think of this is, think of this omega p as any classifying space. It's secretly, I haven't said that, secretly equipped with a universal p form. Assume we have some space, like it's again a bootstrap thing. We wish it existed, and in a moment it will exist. So assume omega p were a space on which a p form existed, such that every other p form in the world could be obtained as a pullback of that one. And we're just forcing that to be true now, right? So we're saying if we have a map or had a map from Rn to this classifying space, well, then we could pull back that form. We would get a form on Rn, a differential form, and by our assumption that that form we're putting back is universal, every form arises this way uniquely. So the set of plots is then identified with this forms they're putting back. It's again wishful thinking, becoming a reality, because you can now check by a slight variation of the unit lemma and some covering theorem that if you have an actual smooth manifold, then the maps into this classifying sheaf are the forms on X. And of course, if you paid attention in Gregory's talk, he amplified very much that one must be careful in carrying this too far. It turns out if you do apply this omega, if you map an infinite dimensional Fréchet manifold like a jet bundle into it, there are subtleties in the different notions of differential forms, and it becomes subtle in which sense this is still the classifying sheaf. But for manifolds, it works. And in particular, it works in the following case, which I do want to highlight, because it's kind of a very cute example of this general machinery, just in kindergarten style resolving a puzzlement that I think it's fair to say so puzzling to the physics community that there's almost no reference that actually says how to resolve it. It's not quite, of course there is. So many of the subject, there's an article by Fried where he essentially says how to do this. Namely, there's the following thing, which you will always hear when you talk to modern physicists in field theory. At some point or later, if they want to be impressive, they'll talk about the anomaly polynomials that they've computed. So essentially, what happens there? There's some field space, and we saw this is a smooth set of maps from Xn. So this is not a power, this is just to indicate the dimension because it's important. So this is meant to be an n manifold. So suppose we're on an n-dimensional space-time, say, and we have fields with values f. And then turns out there's some of these formal local coordinate arguments that make physicists say, here's a differential form, and we call it the anomaly, and they want it to vanish, but the issue is it does not a priori vanish. And then you check, and they tell you, oh, it has degree n+2. And this is in many textbooks, it just appears this way, and you're like, okay, wait a second, so we're on an n-dimensional manifold. Where's this form of degree n+2 that allegedly does not vanish? And the way it works here, we see it now by this definition of this smooth set of differential forms. There are actually in the mapping space, so there's no non-trivial maps from X, no single maps from Xn, omega n+2, it's just a zero map. But in the mapping space, there actually are non-trivial elements. The reason being that in the mapping space, everything is not parameterized. So we have to look at what this map does here, or a map of this form does, on plots. Well, on a U-probe, we're actually not dealing with a single field, but always with a family of fields. In this case, a U-parameterized family of fields, as we saw before. And then it turns out this computation that physicists do, that reads in the fields phi and outputs a form is actually defined in terms of families of these fields. And that form is now actually, by that same reasoning as this field was not actually defined on Xn, but on sort of a U parameter times Xn, Now the differential form, it actually lives on x to the n times u. That can have higher dimension, will have, if u is right larger than r to the n, r to the 2. So you see, but this is exactly a differential n plus 2 form on xn times u. That is exactly what a plot of this mapping stack is, if you just unwind now the definitions we gave. And then, okay, and so forth. And now they want to assume there's some convex support, and you can integrate this. And in total, after you integrate over x, now you have this free-floating 2 form here, which somehow is nowhere, you would think. This is just a modular stack of 2 forms. But in total, we produce a map from the field space to the sheaf of differential forms. So this map, again, has actually the interpretation of being a 2 form on the field space. And that is what physicists would call the curvature of the local anomaly. So that in a more sophisticated discussion that I'm not giving here, you would play an analogous game, not just with these forms, but with actual line bundles on the field space. You would end up with a complex line bundle on field space, which you would have to trivialize and so forth.
So is that, I just don't get this middle term. Is that such a differential form on xn or something?
So I didn't explain this term. This is right. I'm just saying terms of this form appear where you have some operation that reads in what looks like a field, but it's actually a family of fields.
Mm-hmm.
And by some algebra, it produces an n plus 2 form. And then so it's just some n plus 2 form. Imagine you have some n plus 2. And then n plus 2 form.
But that is called a polynomial?
Yeah, they call it a polynomial.
Okay, well, that's what I.
Sorry, I see. Yeah, because these forms, they're in general polynomials in characteristic classes of xn or jargon classes. So it's just jargon. So as you can see, this is aimed at mathematical physicists who are supposed to understand this. So I didn't explain this further, but as I said, the details don't matter at all. It's just this general principle that there's interesting differential forms on these mapping spaces, because there's interesting mapping spaces into the universal thing of different. Anyway, the punchline is here, this is something rather completely elementary actually in terms of math, which solves a major puzzle and that is left open in many, not all, but in many physics texts. And it's just easily, and this is a general theme, it now finds an easy home here. So topos means place, right? So we can say that's where normally polynomials actually take place. Okay, I should maybe speed up a bit, but of course, depends on what we actually want to do. So here's a thing I have to mention in an entry on encyclopedia entry on Topos theory. So if you open math textbooks on Topos theory, they will start out with completely different motivations than what I've given. One motivation you may see is that they say we want a category theoretic home for constructive mathematics, and I want to amplify that also these apparently abstract logical considerations actually all have, well, I don't know about all, but I think anyway. So I'm just showing one example. They do have very immediate and very evident physical intuitive interpretation. And one of these general statements goes so. It's a very general story that some of you, of course, are experts in. Let me just highlight it for those that are not. After Grothendieck introduced the topos as models of spaces, roughly the way I've described it here, there was this category physicist Lavia who watched Grothendieck do this, and suddenly somehow saw that something deeper, in a sense, was going on. He observed that these categories, the Grothendieck called toposes, are actually universes of mathematics in the sense that he observed, so roughly the story goes, every bit of math that you can write to paper, and that is usually interpreted in the usual topos of sets as a construction based on set theory, actually makes sense inside any other topos as long as it's constructive. And constructive essentially means, so I hope the experts will forgive me to make this a bit simplified, it essentially means you're not allowed to use the axiom of choice in its usual form. So what is the axiom of choice? So I'll say in a moment what this has to do with physics. So if you look at what the axiom of choice means, you may wonder, this has nothing to do with physics now. But what it actually means, if you look it up in a set theory book or in a textbook, well, it says something like, if you have an infinite family of sets parameterized over some other sets, we're allowed to choose elements in each of the five. So when I read this first as a student, what are people, why not? I was like, why is this even, it seems hard to grasp if you're not either fully formally minded or maybe have the perspective that I'm presenting now, it just seems nonsensical. And of course, there's a very formal way of understanding why it's not nonsensical. I want to present now a very geometrically, physically intuitive way of why that axiom is actually a problem. Because right, the idea is It's assumed in classical math, but then people say, no, I don't want to assume that. That axiom might be false, and then people fight, like, how can that axiom be false? It's obviously true, right? But here's the thing. So let's write it like this. So suppose B, so let's think about sets. So what does it mean? I have this infinite indexed family of sets. Well, it means I have some index set B, and then I have another big set, which is fibered over B, right? So for each element B and B, where do I have it here? There's a fiber, another set E of B, and my choice means that for each element here, I need to be able to choose an element up here, which sits over that base, right? That's what the axiom of choice in usual set theory. It just means every surjection is a section. But now, so this is the case in set. Now you can have philosophical arguments about whether or not that should be the case, that these dashed morphisms exist. But what I do want to amplify here, that if you think of these sets now as being smooth sets, then this is absolutely unjustified that such a thing should exist. Because we just saw that ordinary smooth manifolds in all of differential geometry sits in these smooth sets. You certainly know, all of you I think, that there are smooth maps of this form called fiber bundles, non-trivial principal fiber bundles. We were talking about principal bundles in the previous talk, which do not have such a section, and crucially not. I mean, that's what makes them non-trivial. So the way to think of this is, even if you assume your axiom of choice in set theory, even then you can choose for every point. So suppose B is concrete, has enough points. So even though if you assume that for every point separately, you can find a fiber here, which most of us do assume, think about it. Even if you assume that, then it's a whole other thing of to declare that you can make these choices smoothly over B. In fact, you will not be able to make them continuously for fiber bundles. So that is the thing. So it will not exist smoothly. So the failure of the axiom of choice, which is one of these things that makes people look into Topos theory, is not something mysterious. It's something if you think about geometric set theory, if you wish, it's the first thing you want to do, not to trivialize the entire physics. So if you wish, that failure of the axiom of choice, the rejection of it, is actually the reason why there are non-trivial bundles in physics, which is, right, if we want to be dramatic, it's the reason why there's anything like flux quantization, solitons, instantons, fermionic anomalies, all these things, they're all topological phenomena, physicists say, by which they mean they're all witnessing the existence of some non-trivial bundle. If you did force the axiom of choice, all this would collapse. WZW terms are of this form. They are meant to, you can actually measure them in the lab. They are meant to encode the anomalies in the standard model. Anyway, so this is real stuff, right? So we don't want the axiom of choice. And so the idea is that now you want to ask, well, what are models of math? What are topos, places where math can take place, where we don't assume the axiom of choice? And these are toposes. And by way of, I guess I'm out of time already. How does it work? And so we will now build, or would build, a system of ever more generalized categories of physical spaces, which eventually all become toposes after this line here, or higher toposes, inside which, as these gray annotations are meant to indicate, inside which eventually we find the right place for many of the things that physicists want to do. Just to amplify, for instance, something as fundamental, as mundane, one might say, as the field space of QC of quantum chromodynamics, which is certainly something, it's not a speculative, it's not string theory or something. It's the theory that makes stuff. Right.
It's being blocked.
Oh, I see, thank you. Oh, sorry, I keep not paying attention to that. If you really ask by what I said before, that field space certainly not in Frechet manifolds, even if you disregard the quarks. But if you regard these quarks, then you need to make sense of these quarks will be fermions, so they have this funny anti-commutative properties. So you have some manifold now, some space, which is hugely infinite dimensional, and at the same time has a funny anti-commutative property, and you want to make sense of this. And the claim is that actually does essentially only work in this topos of smooth codes. I should amplify at this point. This is all, of course, very much connected to what Gregor was talking about 2 weeks or a week ago, to this series of articles that are currently still being written. But yeah, but that's maybe a question.
I think that dashed line that says higher toposes go here should be horizontal instead of vertical, right?
I think it's the topos line. It's not the topos before that.
Oh.
Higher topos. I do mean
Topos is in that direction, not higher in that direction.
Also higher.
Yeah, all high, everything that has a topos or a higher topos is
Is
here.
there.
I think it's correct.
I guess
Right.
higher is the horizontal line is higher.
You know, it's not
Topos
actually
is-
quite. I started arranging it ever more geometric properties to one direction, ever higher gauge symmetry to the other, but then it didn't quite fit. So it's not quite as symmetric as you might hope. But it does fit on the page. That's about it. So this is the topos of smooth sets that we've been talking about. Then I've already alluded several times to the super smooth sets, which maybe we have time to briefly talk about. And then here comes the higher groupoid version. So this is essentially at fermions, you go in this direction. At gauge bosons, you go in this direction. At both of them, fermions and higher gauge bosons, you go in this direction. So what do you think? Do we have 10 more minutes? Something?
Yeah.
Okay, so this is just a small picture. In fact, at the end, you see there was more in that. We also want this quantum aspect, but this is the geometry of physics.
So, can I ask a really naive?
Please, yeah, that's exactly.
The fields give you particles, is that right?
Sorry, say again.
Fields give you particles.
Yes.
Fermion, bosons, quarks. I mean, you're mentioning what I think of them as particles,
Right.
but then the whole theory is about fields.
Yeah, it's a long story. So
Oh,
the
so
way,
there's a-
the
yeah.
way it goes, if you start with the usual Lagrangian field theory, the way Gregory last time explained, you start with these what's called classical Lagrangian theory, where the bosons and the fermions are just fields in the sense I described. They're maps from space-time to some generalized space. Then comes this magic step called quantization, which does something, and that's where these fields become particles. Roughly, you expand these fields, very roughly, you expand these fields in Fourier modes, if you can, and then you call each mode a particle. That's the trick. Yeah, Gregory.
One should say in particular, you cannot really do this in your space-time is not something super nice, like Minkowski, where you can do these expansions in Fourier modes. It's an arbitrary manifold. You might not have particles at all.
Right, so Gregory is pointing out that the notion of particle that seems so obvious to us, it's actually, if you look at the foundations, it depends on assumptions, for instance, on Minkowski space. In models of cosmology, where there's no flat space-time, there's not actually a notion of particle. It's certainly not a preserved one. It has to do with, many people don't realize actually how mysterious this is, but one of the most basic facts in cosmology on expanding space-time, neither energy nor particles actually conserve. Energy appears out of nowhere. Particles can appear and disappear. So the notion of particle is kind of a very specialized one for if you're in a lab and we have very controlled control over, is that a good word? Over our fields, then we can say, okay, that excitation of the field is a particle. So the notion of particle is not very fundamental. If you actually dig into it, it's so I think there's a book even, or at least an article by a famous mathematical physicist whose name I have now forget. It's called Against Particles or something. And so he writes this whole book, arguing, of course, for algebraic quantum field theory, saying we should not base quantum field theory on the notion of particles. Sorry, does this
Yeah, that's precisely what I was kind of confused about.
Yeah.
Right. Yeah. All right.
So field theory is maybe certainly the more fundamental thing. In good situations we have sometimes. All right, so let's see. Okay, so yeah, I want to do this example here because I have to mention this in a review of Topos theory because this was one of the original theorists. I don't think mathematicians fully realize this. So Levier, I mentioned Levier's name, who is the mastermind behind this idea of regarding Topos theory as a form of logic, of formal mathematics done in different mathematical universes. But also at the same time, remarkably, actually he was motivated by physics. Actually, my understanding is from reading some biography, before he became the most abstract mathematician in the world, he was actually a student in a physics department. And the story is really funny or interesting, because apparently he was told to do some computation in electrodynamics for some. He had to do something with vector fields in the sense of electromagnetic vector fields. And so the professor apparently, the way I understood this story, this anecdote, being a physicist, he didn't think much about vector fields. That was clear to him. And so he assigned the student Levier some exercise doing with this. And Levier apparently went home and thought, what is a vector field? What is a vector field? And he thought so deeply about this. That's how he describes it. I think it's on the NLab page. You can read this up. And eventually he left that physics department and went to some category theory school and invented this, or eventually this became what Levier called synthetic differential geometry. So Levier eventually understood, which is very much to the point that I'm trying to make here, that kind of the natural home of differential geometry is in some topos. And I'll explain this now. It's a beautiful story, because if you've ever sat, as some of you did, in the physics lecture, I vividly remember our experimental professor explaining exactly this to us. Like, he would explain to us how to compute like the area of a circle, of a sphere, all these things with exactly this arithmetic. And the funny thing, it actually works, but they wouldn't know why. So, you know, a standard argument in physics textbooks, and much more, even more so in engineering, is you say, oh, here's a quantity, it's really small, right? And if you have a small number, smaller real number, say smaller than 1, of course, it's square, it's even smaller, right? It's cubed, it's even smaller. So in physics, you do something like you say, oh, this epsilon is really, really small. You know, it's actually so small, if I square it, it's actually equal to 0. I'll just behave it if it's 0. So they just do it. It's again a coordinate manipulation, even though they won't say it this way. It's of course easy to make sense of this again in local coordinates. As a mathematician, you say, all right, you want to enforce epsilon squared with 0. Well, you're dividing out the ideal. You're actually in the ring, in the polynomial ring. You could actually take smooth functions here. Say a polynomial ring. Think of this as functions on one variable on the real line. But you want to enforce that your function is actually so small, or never takes values larger than that you even have to consider its square. So you divide out, you say epsilon squared is actually equal to 0. So this is an algebraic construction, which you can certainly do. And then you can say, okay, I made sense of the physicist now. But the issue is the physicists didn't just mean it as some algebraic definition. They mean it as an actual statement about space. And in space, there's no, which coordinate are we talking about, right? You need to choose a coordinate and then which one. So and this is where Topos Theory does it for us. But what we just learned, it's not obvious what we want to do. We want to take these formal expressions, these algebraic expressions, as being characteristic of our probe spaces. That's what locally is the case. And then with the Topos Theory, generate our generalized spaces for this. And we just need one more ingredient, call it one of the 3 magic facts of differential geometry. It's not super widely known. Turns out that smooth manifolds actually faithfully reflected, or the smooth maps between them faithfully reflected in the algebra homomorphisms they induce on smooth functions. Let me break this down. So where should I point to? So suppose you have we're talking ordinary differential geometry now, no topos. You have a smooth function between 2 smooth manifolds, F. And certainly you have the algebras, the real algebras of smooth functions. I just mean the plain real algebras. For those who've seen some Topos Theory, they might think I'm talking about the smooth algebras, the co-presheaf algebra. No, I just mean the plain R algebra of smooth functions on Y and those on X with values in R. And then of course by pullback, by precomposition, I hope that's clear, right? So smooth functions on Y, pull back to smooth functions on X. That's an algebra homomorphism. And this theorem says what we would call Milner's exercise, because it appears first, maybe, or early in some Milner textbook as a side remark, that is actually bijective. So clearly F induces F star, the same as actually F star, this unique F such that any algebra homomorphism between these algebras comes by pullback. It's a remarkable statement. It's remarkable for the reason that it makes differential geometry be so much closer to algebraic geometry than you would have had any reason to hope it should, given the basic definitions. Right, so this says, this is a projection between home spaces. It says that smooth manifolds form a full subcategory under forming smooth functional algebras of the opposite of the category of commutative algebras. Commutative is not some, it's just even of R algebras, but of course it's a particular commutative. But that means for us who are now looking for generalized probe spaces, that says, oh, okay, so here we had in particular Cartesian spaces in bed now. So these were good probe spaces, but look, this category is much larger. We just have opened a new world of possible probe spaces here. If you just declare other algebras that don't happen to be in this image to secretly be the algebras of functions on generalized coordinate charts. So this is exactly the philosophy, the idea of algebraic geometry. Define your space by what its functional algebra is. And so I define now, I'm always undecided about this terminology. At some point we should need to make up our mind, but here I'm calling it now thickened Cartesian spaces. I think the good word would be halo. These are halo Cartesian spaces. Anyway, so I'll now define a category of generalized coordinate charts. I denote them by Rn times d. This d is for disk. It's meant to be the infinitesimal disk, dimension m, and infinitesimal order k. And so you see what I'm doing now is I'm declaring a full subcategory of this, a larger full subcategory of the category of commutative algebras, where I say not just are the smooth function algebras on Rn in there, as we had before, but I allow it to be tensored with polynomial ring in M indeterminates, and I quotient out this is shorthand for any k plus first power of any of these epsilons. So I say, if I say these epsilons are jointly so small that if I multiply k plus 1 of any of them, the result equals 0. You should think of this as now being the algebra of functions. This piece is the algebra of functions on Rn, and then tensor means we have also algebra functions on this infinitesimal disks, but it's so small that it satisfies, its function algebra satisfies this relation. So this is really the trick of algebraic geometry. This is how you would define a non-reduced scheme, for instance, too. But we can now implement all of this in differential geometry due to Milner's exercise here. And so we easily make these thick Cartesian spaces in a side by just saying, well, covering is just the ordinary notion of covering just on this Rn factor, everything else sort of remaining what it is. So there's a notion of coverings here. And so we're entitled by just the general procedure that I started the talk with to a topos, which I'm not calling formal associates. I'm undecided about how to call this differential. Sometimes, anyway, these are like infinitesimally thick and smooth sets, just a sheaf topos on these larger probes. So in this larger topos, you see manifolds are, of course, just to amplify. This is a tautology, but they're still on a uneta, or an extended uneta, if you wish. Oh, there's a comma. They are still faithfully embedded now under this algebraic notion. So if I have an actual smooth manifold, I need to say, what does it mean to probe it by an infinitesimally thickened Cartesian space? But I just say, well, it's just the reverse. Just say, well, it's algebra homomorphisms from the algebra of smooth functions of x to this enlarged algebra that I just defined, which contains these infinitesimals. Okay, so one has to work with this a bit to get a feeling for it, but certainly the definition should be kind of evident. And now this is a context, like a dream context for people like Sophus Lee, if you know this, the founder of Lie theory, actually wrote in Private Communication that he, I don't know how strongly he put it, that many or all of his theorems that he proved, he actually first saw, I don't know if he used the word synthetic, but he writes something like, I first see them by thinking of actual infinitesimals. Then, since I don't know how to make this rigorous, I rewrite in the usual formulation. So in this topos, and there was the Urs driving insight, I think, at some stage in the 60s, is that in this topos, this dream actually becomes true. In this topos of formally thickened, smooth sets, ordinary manifolds exist alongside these halos, these infinitesimal halos. Just to amplify the most basic example is if you take the 1-1 halo, so that's the infinitesimal interval, if you will. It's the infinitesimal 1 disk, so this is an interval in R1 of first order infinitesimal. So it's just the tiniest possible neighborhood of 0 in R1 in this algebraic sense. And now in this topos, since we always have these mapping spaces by the same formula that I showed in the example of smooth sets, can form the mapping space from D1 into X. And a not so hard computation using a second of the magic properties of differential geometry, namely that vector fields are the same thing as derivations of algebras of smooth functions. Anyway, you compute that this mapping space is actually, in this topos, isomorphic to the tangent bundle of X, which is exactly what you should naively expect. You're mapping an infinitesimal interval into your space. You pick some point and then it goes in an infinitesimal direction in some direction. It's a vector, should be, and it is in this case. So proceeding in the spirit, and Gregory talked more about this last time, one actually finds that traditional variational calculus, which is used to find the Euler-Lagrange equations of motion and classical field theories, which also has some funny pitfalls to it that every student stumbles over who learns this, finds its natural home in this topos, which I'm not going to explain. It's just a kind of announcement. We have time for one more. Okay, maybe I should, I don't know. Should we? I haven't really talked about higher toposes yet. What should we do? Should we do fermions?
Maybe higher topos.
Yeah, so a similar trick can now be played with the fermions. We just saw epsilon square can be enforced. We play the same algebraic game to enforce intercommutativity. Then you find fermions. Right, and as I said, there's two fundamental fields in known physics, fermions and bosons. Bosons are also called gauge fields. They have this funny property that, I'm just giving a super kindergarten introduction to homotopy theory, but it's maybe good to see it in the same language that introduces general space, because it actually follows the same pattern. So the idea is now we want to be speaking about field spaces that have the following funny property that if I have 2 points in them, called fields, phi and phi prime, they might be nominally distinct and yet identified by gauge transformation, which for the moment I'm just denoting by this suggestive picture here as something of gauge transformation, which somehow goes from this field configuration to this field configuration and identifies them. This gauge transformation one easily sees, if one follows the physics text, one sees they're composable. If you have transformation from phi to phi prime by g, and then further by h to phi double prime, you get a gauge transformation phi to phi double prime, and they're crucially invertible. That's what makes them qualify gauge transformation. These things are actually isomorphic. And so that, of course, means that now, remember this field family really was a plot of the field space. So that now means that for gauge fields, our plots should no longer form sets. There's no longer a set of plots. There's now a groupoid of plots. There's a set of plots together with gauge transformations between them, which form the satisfy the axioms of the category, with inverses for homomorphisms. So they make a groupoid. But we want to go even higher. Well, some people certainly do. There's also higher gauge fields, certainly in string theory and supergravity, and also, if you believe contemporary solid state physics, also in crystal materials that we find in the laboratory, it may happen, certainly you can consider this as a mathematical possibility, it may happen that even these gauge transformations themselves may be nominally different and yet be identified by higher order gauge transformation. So I'm indicating this by this diagram here, such that they satisfy some analogous properties, which I'm indicating in this picture here, which you've all have seen. I just want to amplify that this is, of course, a phenomenon which is probably even before, or maybe at around the same time, well, a little later maybe, that mathematicians became serious about higher homotopy theory, that physicists certainly ran into this. So they have a model for this, where they describe these gauge transformations infinitesimally by differential graded algebras called BRST complexes. And in these BRST complexes, kind of the ordinary fields are accompanied by what Feynman originally, so this must have been 40s, called gate ghost fields. So in physics jargon, the infinitesimal version, so this is a field, in physics jargon, the infinitesimal version of this, so phi and phi prime is sort of infinitesimally close, much in the way I just described, would be called a ghost field, and this would be a ghost of ghost field. I'm just amplifying this to highlight again how close the match actually is. We're not forcing identifications here. These mathematical structures that you're also familiar with, homotopy theory, match very closely what is actually needed and has been needed in physics. But of course, as the name ghost field suggests, people were uneasy about their conceptual nature. So, okay, I guess I should really come to an end. I just want to amplify now that, of course, what we're going to do is we're going to say, okay, how do we understand now the plots? I'm just calling again. It's hard. How do we understand the plots of these gauge fields? And the idea is we again use probes. That's the idea. We again say, do we have a good picture of this actually? Maybe we don't have a good picture now. I just want to amplify that in saying now that these plots of higher gauge fields form a simplicial set. We're really very much in the same spirit of these probes now, because what we really want to say is, okay, the probes of a higher gauge field space should not just be sets. They should be sets of fields. There should also be edges in there. There should be triangles in there of this form and higher tetrahedra. So how do we understand this thing of plots? Well, again, by probing, we say it's whatever it is, it must be possible to say what are its probes by triangles. How many triangles can I find in there? And I must be able to ask how many tetrahedra do I find in there? Of course, if you just think about what this means now, this language just means these collections of plots of high gauge fields should form simplicial sets, pre-sheets on the simplex category, and so on and so forth. This way one goes further through the lower physics. So maybe the punchline here is that it's the gauge fields and the higher gauge fields that make physics talk homotopy theoretic. So in particular, we find them smooth higher groupoids in this fashion that may be probed both by Rn's and by simplices, which classify Young-Mills fields, B fields, C fields, RR fields, and a whole lot of physics suddenly finds its very natural place in this language. Yeah, I guess I'm out of time. I'll stop here. Thanks for the debate.
Thank you. Any further questions, Urs?
Very nice. That's all. Okay. Topos is the
So I have a conclusion here. Where you function this. So quite contrary to superficial perception, higher Topos theory provides just the mathematical context that physicists so often intuitively but informally assuming anyway. Realizing the higher Topos theory is a wealth of new powerful mathematical tools addressing many of the notoriously subtle issues in mathematical physics and opening the door to rigorous attacks on some of the outstanding properties of the field. I should say, actually, this also goes in the other direction, right? It's also that I think lots of math gets inspired this way. I mean, like I skipped over all the discussion of K-theory. I think the reason that K-theory actually became prominent even among mathematicians was very much that Witten said it's actually needed in physics.
That's good.
Yeah.
It's about something you didn't cover though, which is on the screen now, about this the negative dimensional spheres.
Yeah.
And this, are you seeing it of the same form, that it's sheaves on a parameterized spectrum being sheaves on a site?
Yeah, absolutely. So this is actually what I'm showing here is an exegesis of what André Joyal discusses in his notes on logoi, which is the first written account of this observation that parameterized spectra again form a topos. The idea was due to Biedermann, but just verbally apparently over a coffee break to Joyal. And Joyal indicates this is how to see it. So first you observe that parameterized pre-spectra actually form a higher pre-sheaf category. And it's by this, so consider this category. I mean, I'm just inventing, of course, these symbols here, which I think are suggestive. Just imagine a 2,1 category, which is kind of schematically indicated here, right? It has these objects, point, 0, -1, blah, 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 has these maps, and crucially, it has freely these homotopes. And a pre-sheaf of this, think of what it is, right? A pre-sheaf of spaces of this. So it's for S0, an infinity group point, for S-1, infinity group point. Now the arrows get reversed, so they sit in a square like so, which of course means if you form the pullback, that this space E0 now has a map into the loop space of the space that is associated here. So you get exactly this map from mapping this square. That's all it says. And these edges just mean everything is pointed in the sense that it's in, what's it called, an X space, right? It's a section space. And so this gets pre-spectra. So an object in this pre-sheaf infinity category is a sequential spectrum. And then the observation one has to make is, which Joyal describes, one just has to observe that the spectrification of this is a filtered co-limit. The spectrification essentially means you take the co-limit overtaking omega. And filtered co-limit, so this, right, this is a reflective subcategory now. Sorry, no, yeah, we take the filtered co-limit. So this will produce a localization that commutes with finite limits, since it's a filtered co-limit. And that means the subcategory that we localize on is again less reflectively embedded, and hence is a topos. That is the argument. It's a rather simple argument, actually. I mean, compared to, I mean, what you have the ingredients, right? It's just a few lines. And I think, I was just thinking about if you think about what this actually does, I think the right intuition here is that you throw in the negative dimensional spheres. In fact, I think the representatives here, they come out as the sphere spectrum shifted this way. Of course, so for instance, take S0, right? The thing that is represented by S0 is, of course, just comes out as S0, but then we have to spectrify it. That makes it the sphere spectrum.
So representable on S0.
Right, because it has the S0 receives maps from itself, that is the identity, and it receives a map from the point. So.
But I mean.
So S0, the representative of S0 actually sends on S0, it takes the value S0, and on the others, it's empty. So it's just the pre-spectrum, which has S0 in degree 0 and nothing else, but the spectrification of that is sigma infinity of S0, which is a sphere spectrum. And I think it works, yeah, so.
Okay, any other questions?
Maybe how is this related to quantum?
Yeah, that's just what we were just talking about. So the story goes, the way I'm the scrolling is almost. So the way I'm motivating it here, which is actually sounds informal, but it's actually sort of correct. So physics is ultimately quantum, of course. So where quantum state spaces are linear spaces. So let's just think deeply about what it means for linear space. So apart from any other things it might mean, fundamentally it means you have an abelian group structure. That's what linearity means, right? Abelian groups are linear. So now in homotopy theory, the point is, which actually I haven't talked about, but some of you of course very well know, is that there's not just non-abelian and abelian, but there's a whole spectrum. I shouldn't say spectrum here, a whole gray shade of grayscale of different notions of effectively the more you can deloop. So if your space is a single loop space, if you're infinite group, then it has a group structure. If it's a double loop space, it has a little bit more abelian groups. So the fully abelian groups should be those things, E0, that are loop spaces of arbitrary order of something. And that's just what we're enforcing now in homotopy theory. So we want to say E0 is sort of a fully abelian infinity group. And we say it by saying, okay, it's equivalent to a loop space, which in turn is equivalent to a loop space, and so on ad infinitum. And that turns out to be a spectrum. So the claim here is that spectra, in the direct topological sense, are sort of the analogs, the homotopy theoretic analogs of abelian groups, fully abelian groups. And so then inside there, you maybe have a chance to find quantum structures. In fact, you do. One of the simplest things one can do is you take an Eilenberg-Lagrange spectrum, or HC, and its module spectra are complex chain complexes. They're hard, as one says, so the kind of the zero truncated category inside there is just a complex vector space. In this sense, the complex vector space of quantum mechanics that you might want to see actually start to live in this topos, calling single.
Okay. And with that, okay, let's thank Urs again for the very nice talk. Speakers and audience.